This instructional video series provides a university-level education in English for learning about environmental and carbon-neutral issues. I am Satoshi Kaneko, Director of the Mie Global Environment Center for Education and Research at Mie University. The IPCC, or Intergovernmental Panel on Climate Change, releases assessment reports every few years. These reports are published by three working groups: Working Group 1, Working Group 2, and Working Group 3. Working Group 1 deals with the physical science basis of climate change, and its sixth assessment report, or AR6G1, was released in 2021. Working Group 2 addresses impacts, adaptation, and vulnerability related to climate change, and its report AR6WG2 was published in 2022. Similarly, Working Group 3 focuses on the mitigation of climate change, and its report AR6WG3 was released in 2022. In understanding the IPCC AR6WG1 Session 1, you will learn about the physical science basis of climate change by exploring the Sun and Earth energy balance, the carbon cycle and the atmosphere, and the human impact on the carbon cycle.
Welcome to our class on understanding the latest IPCC assessment report. In this class, we'll be looking at the physical science basis of climate change. That's the AR6 from Working Group 1. It was released back in 2021, and this report contains the latest research results since the previous report was issued back in, it was 2013. That was the AR5. So hi, my name is Dan Bin, and I will be your guide for the next two lessons as we navigate this important yet really complex report. So if you've had a chance to look over this report, and if you haven't, I really recommend you do, because you'll see a bewildering amount of information here. And it might look really complex and confusing. Well, that's because this document is primarily designed for experts already in the field. These experts are looking for the latest updates. This is not really designed for the public or non-experts wanting to know more. But by the end of today's journey, I hope you'll have a solid and high-level understanding of all the key concepts in this report, so you'll have the confidence to explore this report and other reports on your own. This is the roadmap we'll be using for our class. It's going to take us on a journey that connects the dots between human activity on one side and the climate response on the other. Now, the first stop on our journey is going to be the Earth's energy balance. This is how much energy is coming from the sun and how much energy is leaving the Earth. After that, we'll go and look at the greenhouse effect itself. This is the chemistry in the atmosphere that plays a key role in regulating the Earth's temperature. It keeps it from being an ice ball, really. And then we'll go back in time and see how that chemistry has changed ever since the formation of the planet, and then most importantly, see how humans have played a key role in changing that chemistry, especially over the last 100 years or so. And then we'll close up our first section by hearing from one of Japan's leading researchers, and he's a prominent member of the IPCC's Working Group 1. He's been involved in this for decades, and is a super nice guy. In part 2 of this class, our journey is going to take us into the world of measuring and modeling the Earth's climate system. So over the past 100 years, our modeling and measurement tools have really come a long way. We now have powerful measurement tools like remote monitoring stations connected to the internet, we have satellites with amazing sensors on them, and we have supercomputers capable of running the most advanced climate models we've ever had. And together, these tools give us a much better insight into what's going on and how to help anticipate the future climate impacts. The next stop on our journey is actually going to bring us back to where we are today. We're going to see how human beings have actually changed the chemistry of the atmosphere. We've been doing that for quite a while, but we're now seeing that chemistry is actually affecting the climate, sometimes quite severely. And we'll discuss how researchers have unraveled the complex web between the natural drivers and the human drivers. So some things are caused by human beings, but there's also a lot of natural variation. And teasing those apart gives us deep insight on connecting cause and effect, cause being humans and effect being also humans sometimes. we'll get to meet another one of Japan's leading climate scientists. She's focusing her work on extreme weathers, including typhoons. Now, she's looking at trying to detect the difference between the natural variations and the human-caused variations, and by separating that out, can help create models that can help us do a much better job predicting the future. Finally, the last stop on our journey will be looking ahead to the choices we have to make. We'll be using the 5 key scenarios from the IPCC. These are the Shared Socioeconomic Pathways, the SSPs, and we'll be using those to examine the likely consequences of the various choices we can make. And while this is the last stop on our journey here in the class, it will be just the beginning. And I hope you will have the understanding and confidence to be part of these amazingly important decisions that need to be made. So, without further ado, let's get into the class. The first stop on our journey to understanding climate change is the Earth's energy balance. The Earth's energy balance is what drives the entire climate system, and as we shall see, is an incredibly important part of the big picture. The good news is it's actually very simple to understand. The Earth's energy balance is simply the difference between the amount of energy coming in from the sun versus the amount of energy the Earth is then re-radiating out into space. And it's this balance that drives the entire system. So that's where we're going to start our journey. So first we're going to talk about the energy that comes from the sun. This energy basically comes in 3 categories. One of them is the visible energy, what we call light, and that's pretty much what a lot of people think about when they think about the sun's energy. However, there's also energy that comes from the sun that you can't see with your eyes, but you can feel with your hands, with your skin, and that's called the infrared energy. And the last category is the energy that comes from the sun that you can't see and you can't feel, and it's called ultraviolet. Well, you can't see it and feel it immediately. If you have fair skin and you have spent too much time out in the sun, later that day you may both see it and feel it as a bad sunburn. So we just looked at the quality of the energy. If we look more at the quantity of the energy, we'll see that about 30% of it is actually reflected back out into space. And it's being reflected by the clouds, ice sheets, snow, and lighter colored rocks and soil. But 70% of that energy is actually absorbed by the Earth itself, by the oceans, the land, and the atmosphere. And when that energy is absorbed, it's turned into heat, and it's that heat that keeps the Earth from being an ice ball. It keeps the Earth warm so it can support life on Earth as we know it anyway. So you may be wondering, how does all that energy travel 150 million kilometers through the vacuum of space? Well, it turns out that that energy is actually in the form of photons, and that's where we're going next. But exactly what is a photon? Well, that wasn't really well understood until around 1905 when Albert Einstein published his work on the photoelectric effect. And in that paper, he introduced the idea of a quanta of energy, these little small packets of energy. Today, we call those photons. And for this discovery, he was awarded the 1921 Nobel Prize in Physics. These photons travel from the sun to the Earth at the speed of light, which isn't too surprising because what we think of as light is actually just made up of photons. And it takes about 8 minutes, 20 seconds for those photons to reach the Earth. But what would have happened to those photons if they hadn't hit the Earth? Well, they'd just keep going out through space until they hit something. In fact, they can travel millions and millions of light years into deep space. There's no real end to a photon's life unless it hits something. So if you go out at night and look up at the stars in the sky, you'll see that starlight is just photons coming from stars far, far away, similar to our sun. And those photons have traveled millions and millions of light years to get here without hitting anything at all. That's pretty amazing. Well, they didn't hit anything at all until they hit our eyes, and, well, that was the end of the photon, but the beginning of seeing something. So that's how a photon works. There's a very powerful tool for understanding and thinking about photons. It's the spectral curve, or sometimes just called the spectrum. And we can think about the spectral curve sort of like a musical keyboard with the various photons represented as different notes on that keyboard. And by plotting the frequencies, we can create these spectral curves, and that kind of reveals the fingerprint or the characteristics of the actual light that's coming from the sun, or wherever it's coming from. And we're going to put the lower frequency, lower energy photons on the far left, and the higher frequency, higher energy photons on the far right. Sort of like on the keyboard, the lower notes are on the left and the higher notes are on the right. But this isn't just an abstract concept. It's a tool that allows us to see, measure, and understand photons that we can't see with our eyes. But we will be seeing a lot of this curve. So we've seen that there are many different kinds of photons out there, the ones we can see and the ones we can't see. So let's take a deeper look at the photons we can see, the visible photons. Now they come in a wide range of energy levels too, from the low energy colors, the reds, the oranges, and the yellows, all the way up to the higher energy photons, the higher energy colors, the greens and the blues and the violets. So if all those different photons arrive at your eye about the same time, your eye will perceive that as being white. But there's no such thing as a white photon. It's just a mix of all those different photons striking your eye at about the same time. What about the photons we can't see, the infrared and ultraviolet energy photons? Well, they too come in a wide variety of types, but since we can't see them, we don't have a lot of words, a lot of common words anyway, to describe them. So we'll put those on our spectral curve. And this is where the spectral curve comes in really handy. And if we put that infrared energy onto our spectral curve, we'll see that it all lies to the left side of the visible range. That's because it has lower energy than the visible light. And this infrared energy can be further subdivided into various categories. We often call them bands, such as the IRA, this is infrared A, infrared B, and infrared C band, as well as the FIR, that's the far infrared. And these bands are very important when we look at how the atmosphere interacts with these photons. The same is true for ultraviolet energy photons. The ultraviolet photons, they have more energy than visible photons, so we put them on the right side of our rainbow. And they too can be divided into several bands. You've probably heard of some of these. There's the UVA, the UVB, and the UVC. The UVA is relatively safe and it can lead to tanning of your skin, but it's the UVB and the UVC that can damage the cells in our skin and cause trouble. The UVC is particularly dangerous, but fortunately most of those photons don't actually make it through our atmosphere. How to make a photon? Well, there's a lot of ways to make a photon, but probably the easiest way is the fact that warm and hot objects all emit photons. Any object that's warmer than absolute zero emits some level of photons. And so we can actually make those photons in our kitchen. So if you have an electric stovetop like this, it's kind of an old one. So you see when I turn it on, at first as it's starting to warm up, you can't see anything. But as it gets warm enough, it actually starts glowing in the red. And if we were going to look at this using an infrared camera, a special camera that can see the infrared photons that we can't see with our eyes, we can actually see that when the stovetop is first turned on, it starts warming up and you can actually see it using the infrared camera. You can see it with the thermometer there too. And at some point it starts glowing so our eyes can detect it. So if we were to add our fancy spectral curve to this situation here, we'd see that even before we turn on the stovetop, there's energy coming from the stovetop, which is kind of interesting, but it's at room temperature, and all things emit photons if they're above absolute zero. However, since everything else in the room is also at the same temperature, at room temperature, those photons just kind of interact with each other, but nobody's winning in that battle. However, once I turn on the stovetop, you'll see it starts warming up and the spectral curve starts moving towards the visible range. And as it gets warm enough, you'll see just a very small amount of that curve goes into the rainbow, the visible spectrum, that visible part of the spectrum. And that's why we can see it. However, a vast majority of the energy coming from that stovetop is in the invisible infrared range. And there's one more tool I just want to point out, and that was the thermometer in the back. This particular thermometer has both centigrade and Kelvin. You may remember Kelvin from a science class. We don't use it too often in our normal world, but in the world of climate change and the world of physics, it's a very powerful tool. So the Kelvin scale, sometimes called the absolute temperature scale, starts off at absolute zero. The coldest temperature any object can be is 0 Kelvin. Now in the Celsius scale, it's minus 273 degrees or so. So that's a very awkward number to deal with. But 0 is pretty easy. So 0 degrees Kelvin means it's at the lowest temperature at absolute zero. This curve is very useful for dealing with very, very warm objects as well. The surface of the sun is about 5,500 degrees Celsius, but we don't really have any feeling for what that is. The surface of the sun is very hot. But in Kelvin, it would be 5,772, and it's that one scale that allows us to go all the way from absolute zero all the way up to the hottest objects in the universe. And that scale can also make some of the physical formulas very easy to manipulate, and we'll see that later in a bit. But there are other ways to make photons at home. So this is an old style, it's called an incandescent light bulb. This is the kind of light bulb that Thomas Edison developed about 150 years ago. And it works by basically the same principle as the stovetop. There's a little piece of metal inside, and when it gets hot, it'll start emitting photons of the visible range. But even before it's doing that, it's emitting photons. So if we add our spectral curve to this, we can see that even when the light bulb's off, it's emitting some photons. Those are these room temperature photons we can't see, and everything's emitting them, and so they all kind of cancel out. But when we turn on the light, it starts heating up rather quickly, and it soon gets to a temperature where it's capable of emitting photons, a lot of photons in the visible range, and that's why it's a light bulb. However, if you look at that, there's a lot more of the energy that's still in the invisible infrared range, and you could think of it almost as a heat bulb, right? That's actually one of the reasons people prefer using LED lights, because they're way more efficient. However, this is how you can make photons at home with some of your household appliances. But if you don't want to be indoors, you can just go outside in the middle of the day and see what the sun is doing. So the surface of the sun is very hot, as we saw, and if you put that on our spectral curve, it's basically the spectral curve we've been looking at. You'll see that it's a whole lot of the sun's energy is in the visible range. So we've seen how to make photons, but what happens when those photons interact with some matter, when they hit an object, for example? Well, those photons can either be transmitted, go right through, and our little transparent Earth shows that, or they can be reflected, as we have here, our very shiny Earth. All those photons get scattered back out into space. Or an object can absorb those photons and take all of its energy and turn it into heat. And at that point, the photon ceases to be a photon. But the energy doesn't go away, so energy never goes away, but photons come and go. We're now going to shift focus from the quality of the energy to the quantity of the energy coming from these hot objects. First, we're going to meet two scientists, Stefan and Boltzmann, two scientists of the 19th century. They helped us understand how a hot object like a stove or the sun radiates energy. They came up with a simple yet powerful equation that relates the temperature of an object to the total amount of energy that object emits. We're now going to watch this curve grow from 0 Kelvin all the way up to about 5,700 Kelvin, the temperature of the sun. This is the Stefan-Boltzmann curve, and it shows us that the hotter an object gets, the more energy it pours out. Notice how it's not a straight line? This energy shoots up dramatically as the temperature rises, to the fourth power of the temperature, as it turns out. Now we're going to put that together with the spectral curve we've been looking at and see how they relate to each other. Here on the left, you'll see the new Stefan-Boltzmann curve again, and on the right, we have the old emission spectrum that we've been talking about earlier. Together, these two curves help us understand both how much energy is being emitted and what type of energy it is, whether it's in the infrared, visible, or ultraviolet. The Stefan-Boltzmann curve tells us about the quantity of energy, while the emission spectrum focuses on the quality. Now let's put all that together and go back to our stovetop. As the stovetop heats up, we can see the total amount of energy and the type of energy it's emitting together. And this relationship between the quantity and quality of energy is governed by the principles we just explored. These rules apply not just to our kitchens, but across the entire universe, from the warmth of our homes to the brilliance of the stars. Now let's explore the balance of the energy between the sun and the earth. After all, that's what this whole class is about. Using the Stefan-Boltzmann equations with the sun's temperature a bit over 5,700 Kelvin, we can determine that the sun emits over 60 megawatts per square meter. Now that's a lot of photons leaving the sun. However, as it travels through space, as those photons spread out over space, They don't disappear. The photons remain until they hit something. The same amount of photons that left the sun still exist, but by the time they reach the Earth, they've been distributed over this much, much wider area. And so the Earth only receives, it turns out, about 1/50,000th of that, so about 1,360 watts per meter squared. Of that energy, of the 1,360 watts, about 30% of it is reflected back out into space. And this remaining energy is roughly about 960 watts per square meter. And that gets spread out over the entire surface of the Earth. So it came in as a disk, and now it has to be spread out across an entire sphere. The math behind that's actually incredibly straightforward. You just divide by 4. And that leaves us with 240 watts per meter squared of energy coming from the sun. And you'll find this number, 240 watts per meter squared, in many publications on climate change. So it's worth remembering because it shows up pretty much everywhere. This energy from the sun is often referred to as the incoming solar radiative energy. And when it's absorbed by the surface of the Earth, guess what happens? The Earth starts warming up. And that's a key piece of our understanding of how the Sun-Earth balance is working. When the Earth absorbs this incoming energy, the Earth begins to warm up. As the Earth warms, it starts to emit photons of its own. And the Earth, you can think of this as the Earth effectively cooling itself by emitting these photons back out into space. So if it was not emitting those photons, well then the Earth would just continue to get warmer and warmer and warmer. Eventually, the Earth warms enough to emit 240 watts per meter squared of energy back out into space. And this is what we call the outgoing radiative energy. And at that point, the Earth is in radiative equilibrium with the incoming solar energy. So what comes in and goes out are now the same, so there's no more change. We can compare our spectral charts here and notice a couple of things. One, the amount of energy from the incoming solar energy and the outgoing radiative energy from the Earth are the same amount of energy, but their characteristics are very, very different. So the sun, because it was initially created by this very, very hot surface of the sun, has a completely different spectral distribution. The Earth, only at this relatively modest temperature, releases most of its photons way down in the infrared. And this is key to understanding the greenhouse effect, which is the subject of our next chapter. But I'm getting ahead of myself. You're probably wondering, what would the Earth's temperature be in order to maintain this delicate balance between incoming and outgoing radiative energy? And that's the question we'll be exploring in the remaining part of the class. If you're still wondering what the temperature would be on the Earth given the radiative balance, you wouldn't be the first one. Meet Joseph Fourier, a brilliant scientist from the early 19th century. So even without the sophisticated tools and measurements and concepts that Stefan and Boltzmann had 70 years later, Fourier's powerful mind led him to speculate that, well, based on his calculations, that the Earth's temperature should be significantly cooler than what it actually was. So he could measure how much energy was coming from the sun and had a pretty good idea given the time he was working on this. And he said, the Earth should be significantly cooler, like maybe 30 degrees cooler. And he kept wondering about that, and he had a couple of ideas on what would cause the Earth's surface temperature to be as warm as it was. Well, maybe it was the internal energy of the Earth, volcanoes and geothermal energy, that sort of thing. Maybe it was the radiation from all the stars. Maybe they added up to be significant. But he also postulated that perhaps it was Earth's atmosphere causing this warming. So using the Stefan-Boltzmann equation, we can see that the Earth's surface temperature, given just the radiative balance between the Earth and the sun, should be around minus 18 degrees Celsius. Instead, it's really a nice warm about 15 degrees Celsius. So about 33 degrees warmer than it would be just based on this radiative equation that we just spent all this time looking at. And that question remained all the way through the 19th century. And here's a spoiler alert. It turns out that it's the atmosphere, and we're going to explore that in the next section.